This is a lecture on wave power. Basically, I'm just going to explain the equations that you'll need to do the assignment questions on wave power. It's chapter 11 in the Twiddle textbook. So just a few comments about waves. The marine environment is an extremely harsh environment to work on. Wave patterns are irregular. Most big waves are far offshore, and their frequency is quite low compared to the frequency that you need to generate electricity. They're often complex and irregular, and as they approach the shore, they do all kinds of strange things. However, just for some basics, we're going to treat them as sinusoidal here. So let's just review a little bit of the theory about sinusoidal waves. So if we have the sinusoidal wave structure like this, we'll kind of get a 3D view here of the wave crest going back like that. So if you recall, peak to peak or trough to trough, the distance here is called the wavelength. So lambda is wavelength in meters. Now the formulae here use peak to trough height, but remember that is not amplitude. So peak to trough we'll call capital H, and so H is 2 times the amplitude, because amplitude is from 0 up to the peak or from 0 down to the trough. So this H is 2 times amplitude, and that is also in meters. And then as the wave extends back in space, this distance here we're going to call L, and that's equal to the wave crest length. And that's also in meters. Okay, now this wave would be propagating in this direction. So V is the speed of propagation, sometimes also called phase speed. And that's in meters per second. Okay, so those are the variables that we'll be looking at. And we know from any wave in general, the relationship between propagation speed, wavelength, and frequency is V equals lambda F, where F is the regular old frequency in hertz. Okay, and then don't forget that that's also lambda over T, where T is the period. 1 over F, and that's the period of oscillation in seconds. Okay, now, this is true for all waves, that V is lambda F, but for deep water waves, there's a special relationship, and that is that the speed of propagation is proportional to the square root of the wavelength. So it's equal to G lambda over 2 pi. So you can use that relationship for all of the problems that talk about waves. Okay, now the power in the wave, I'm not going to derive it here, I'll just tell you what it is. It's often expressed as power per meter of wave crest length. So this gets a new symbol called J, and this is equal to rho G squared T H squared over 32 pi. Okay, so what are all these variables? Rho is the density of water, and it's seawater. So this is density of seawater, which is a little bit higher. It's salty, so it's a little bit higher than fresh water, and we're going to use a number of 1025 kilograms per cubic meter. Okay, because that's because of the salt. G is just regular old G, 9.8. T, that's the period, it's defined right above there. H is that twice amplitude, it's defined, and then over 32 pi. And then the units for J, so this is equal to the power per wave crest length. Okay, so J is equal to the power in the water divided by L. Okay, so that's going to be a useful equation. Now, if we are harnessing this power, there are all kinds of very innovative and interesting systems that harness wave power, and I've put a bunch of videos, links to videos on D2L where you can have a look at some of these crazy contraptions that people have. A lot of them are just models. There are very few places that actually harness wave power, but the Palamas is an example of a giant snake that oscillates up and down on the waves that is generating power, and there's a video of that also. Okay, now the last thing we need to know if we want the electrical power. So the efficiency of all those machines is wildly different. So the electrical power has to do with the efficiency times the power in the water. And so that would be the efficiency times J times L. Okay, where eta is efficiency of wave generating apparatus. Okay, so that's it for wave power.